cantilever beam. I hope that you will see the material itself. So this is a cantilever beam. Cantilever beam is a, it is on. Mic is on. Okay. Yes. So we are dealing with cantilever beam. So that is a beam that is clamped at one end and free at the other end. So what are the boundary conditions? So this is clamped here and free here. So as we said already, for clamped beam, both the function and both the deflection and the angle or deflection angle or derivative of W with respect to x vanish. So that means that at x equals 0, this what takes place. At the free end, bending moment equals 0. Therefore, second derivative of W equals 0. And here, third derivative, that is a shearing force, equals 0. So we have, if you remember, expressions capital W of x equals A1 K1 alpha x plus A2 K2 alpha x plus A3 K3 alpha x plus A4 K4 alpha x. Now when I satisfy the condition at x equals 0, capital W equals 0, I get A1 K1 at 0 plus A2 K2 at 0 plus A3 K3 at 0 plus A4 K4 at 0. This equals 0. But these quantities all equal 0. Okay, there and K1 at 0 equals 1. So from here we get A1 equals 0. Then we have dW dx. This equals alpha times A1. So that will be K0, is it not? Alpha x. But K0 equals K4. Then, so this is alpha times. Then A2 K1 alpha x plus A3 K2 alpha x plus A4 K3 alpha x. Now at 0, dW dx at 0 equals 0, and this equals alpha. Now A1 K4 at 0 plus A2 K1 at 0 plus A3 K2 at 0 plus A4 K3 at 0. Okay? So, but this quantity equals 0. This quantity equals 1. This quantity equals 0. And this quantity equals 0. Okay? Excuse me. So therefore, A1 and A2 equals 0. A1 and A2 equals 0. So what we are left then is A3, K3 plus A4, K4. Then we have at L, two conditions at L. First of all, second derivative of this equals 0. So first derivative of K3 equals K2. Then one more derivative equals K1. So derivative here is K3, then one more derivative is K2. So A1, K2. Additional derivative will be from K1 we will get K4, from K2, K1. So we get these two equations. So again we can write down two homogeneous equations with respect to A3 and A4. In order A3, and we would like to write, in order A3 and A4 not to equal 0 simultaneously, A3 and A4 should not equal 0 simultaneously. Therefore, determinant must be 0. And this determinant equals, you may want to sit here. So we are dealing with clamped free beam, as I said. And determinant equals then K1 times K1, or K1 squared, minus K2 times K4. Equals 0. So if you will expand this, if you will take K1 squared and then minus K2 times K4, we will get the following expression. Cosine alpha L, hyperbolic cosine alpha L, plus 1 equals 0. What is our homework set number? 9 you did, or 9 will be? 9. Okay. Homework set number 9. Derive from K1 squared minus K2, K4 equals 0, the equation cosine alpha L, hyperbolic cosine alpha L, plus 1 equals 0. So please, that is first part. Okay? We get this following equation. Now, this equation can be solved, of course, numerically or graphically. Graphical solution is like this. So please write down numerical solution or graphical solution. Numerical, that means we are asking computer to do calculations. Graphical, we can use calculator as well as figures. Look, please. So we put here functions. Look, this is cosine function. Cosine alpha L. So this is y equals alpha L. So these are functions, fi. What does it mean, functions? I will explain you. So we wrote cosine alpha L, hyperbolic cosine alpha L, plus 1 equals 0. So we will write the following. We say that this equation is equivalent to cosine alpha L equals minus 1 divided by hyperbolic cosine alpha L. So function f1 equals cosine alpha L. Function f2 equals minus 1 hyperbolic cosine alpha L. Or alpha L we denoted as y, so f1y equals cosine y, and f2y equals minus 1 hyperbolic cosine y. Okay? Are you with me? So then this is function f1. Okay? So this is cosine at 0 equals 1. Cosine of that is pi over 2 equals 0. So that is cosine at pi equals minus 1. And cosine 3 pi over 2 equals 0, etc. Now, hyperbolic cosine starts with 1. Hyperbolic cosine. So it equals e in power alpha L plus e in power minus alpha L divided by 2. So this is such a function. Hyperbolic cosine. Starts from 1 and goes up to infinity. So here is, now this function is, we need a minus 1 hyperbolic cosine alpha L. So at 0, this equals minus 1, so that is this value. Then, like hyperbolic cosine is increasing, that goes to 0. Okay? I don't know what to compare. This is what it is. Do you agree with me or not? Student asked me whether it is like something else. I don't know. Okay. So because we are dealing with this problem, not with anything else. So paying attention. So at this point, there is an intersection. So that means that alpha L that corresponds to this intersection is a root. This root happens to be bigger than pi over 2. It is specifically 1.875. So it is not, pi over 2 is 314 approximately divided by 2, it's 157. So this is on the right-hand side, bigger than that. Now, second root is before 3 pi over 2. So that is, as we know, 3 pi over 2. So this root is a bit smaller, a bit close to that value. That equals 4.693. So had it been here, just there, would be 314 and 157, which would be 167, 471. So if that was that point, that would be 471, but this is very close, it's 469, 4694. So that is graphical solution. But later, paying attention, because this curve, this minus 1 over hyperbolic cosine goes close to 0, then roots are very close to these points. Okay? So for k greater than 2, it is 2k minus 1 over 2 pi. What is 2k? So for k equals 1, that would be pi over 2. 2 minus 1, which is 1, half pi. So that is not correct. That is not a good approximation because it's not 157, but 1.875. For the second, it is quite a good approximation. 469.4, that is an exact solution. Approximate is 471. But for greater values, and this value is here, so it's a bit more than 5/2 of pi. So that is 2k minus 1 over 2 pi. How much are the natural frequencies? Natural frequencies, then, I should take, that is a case value of alpha L. Okay? So that is first value, that is a second value. Then that is a case value. Oh, maybe I should put it down so that we see better. So there is first value is some number, second value is also some number. Further values can be written in terms of pi. So natural frequencies then is alpha L in case, alpha L case value squared then EI over rho A L fourth power. So then we have mode shape. Please write down the mode shape. So that is K2 alpha KL, K3 alpha KX, minus K1 alpha KL, K4 alpha KX. Prove. So I would like to write down this. So that is this homework, second homework. Okay, show that phi k for clamped free beam equals. And I will depict the mode shapes. So these are the mode shapes. That is the first mode shape, second mode shape, and that is a third mode shape. Actually, here instead of capital X's, please write down W's of phi's. Phi 1, phi 2, phi 3. Now, because there is no boundary conditions are non-symmetric with respect to the middle. So there is no symmetric modes and anti-symmetric modes. Because boundary condition here is clamped, here is free, so these are totally different boundary conditions. Now pay attention. This, of course, here displacement equals 0. This is a node, but it is a boundary node. What is a node? Node is a place where the mode shape has 0 value. Please write down. Node is a location where the natural mode has a 0 value. So first mode has on one boundary node. We can write first mode has one boundary node at the clamped end. Now, second mode has one inner node and one boundary node. Third mode has two inner nodes and one boundary node. That is a second mode. Again, second mode has two inner nodes. You may want to write down here inner node, and that is a boundary node. And now we can actually conclude that number of inner nodes, okay, maybe I will write down. The number of inner nodes equals the mode number minus 1. This is a mode number minus 1. This we naturally had also in simply supported case. Now, we can also write down here in this case that pi appears only in asymptotic expression of frequency. Natural frequencies tend to natural frequencies tend to pi square asymptotically. Asymptotically means for big values of k. For big values of k, we get pi. For simply supported case, we got pi not asymptotically, not for high modes, but for also low modes. Any questions? Any comments? So then we will deal with the beam that is clamped at both ends, clamped or fixed at both ends. So boundary conditions are at x equals 0, function and first derivative equals 0. At x equals L, function and first derivative equals 0. Okay, so because do you remember we had clamped free, so clamped is function and first derivative. Now in both cases we have the same set of boundary conditions. So we already had before that A1 and A2 are 0 for clamped end. Remember before that just in previous case we had clamped free. So, but the main thing is that on the left we had clamped end. There we had A1, A2 equals 0. So naturally, because we have clamped end on the left, A1 and A2 again equals 0. So we are again left then with the same expression, W of x, but expressions will be different. A3, K3 plus A4, K4. I think we appreciate that these K functions are simplifying matters unbelievably. Now we would like to calculate to satisfy the boundary conditions at the end. So I write down here L. So I see instead of x in the expression for W of x, I substitute L. I get A3 K3 alpha L plus A4 K4 alpha L equals 0. Then I differentiate this expression. Derivative of K3 will be alpha times K2. Derivative of K4 equals alpha times K3. So derivatives are very easy to remember what the derivatives are. Now I demand the determinant must be 0. So that is K3 diagonal terms. K3 times K3 will be K3 squared. K2, K4 equals 0. So we are getting that K3 square minus K2, K4 equals 0. If we do the analysis, we get cosine alpha L times hyperbolic cosine alpha L equals 1. Or if I denote small trigonometric cosine with small c, hyperbolic cosine because it takes big values with big C, I get CC equals 1. So we would like to add here then homework number 3. Show for clamped case that what we have is cosine alpha L, hyperbolic cosine alpha L equals 1. So this equals 1. And now, so we can again solve this problem, is it not? I mean asymptotically. Now, first of all, we can solve this problem by solving this characteristic equation. Okay, we can solve this characteristic equation. This characteristic equation's roots are as follows: 473, 7853, 10996, 14137, etc. Or we can also have asymptotic approximation, which is k plus half pi. Please pay attention. Even for the first frequency, approximation is very good, because exact value is exact. 473. Approximate is pi plus half pi, 314 and 157. So that is 471 approximately. So it's less than 1% error for clamped beam. And solution actually is found analogously. Indeed, pay attention. For alpha L much greater than 1, hyperbolic cosine goes to infinity. Is it right? Hyperbolic cosine goes to infinity, because it is e in power alpha L, etc. So therefore, this equation cosine alpha L times hyperbolic cosine alpha L equals 1 means cosine alpha L equals 1 over hyperbolic cosine. This right-hand side goes to 0. So the roots go to cosine alpha L go to 0. But cosine alpha L has roots k plus half pi. Okay? And actually the same figure can be made. Okay, I will show this figure. So cosine starts here. Etc. Now hyperbolic cosine, 1 over hyperbolic cosine starts at 1. Okay? And okay, now we have cosine alpha L equals 1 over hyperbolic cosine alpha L. At 0 it is 1. And then it goes to 0. I think, yes, I will use another color. So this is the root. So that is pi, and that is pi plus 1/2 pi, etc. Then this is the root, etc. So that is very close to root of just cosine function, because it is 1 over. Okay? These are the mode shapes. Please depict the mode shapes. Now, first of all, mode shapes. Here, two boundary nodes. One node, second node, boundary nodes. No inner node. Here we have one inner node. Here we have two inner nodes. So we can say that number of inner nodes equals mode number minus 1. Again, we have the same, absolutely the same conclusion. Now, first mode is symmetric with respect to middle cross-section. Please write it down. First mode is symmetric with respect to middle cross-section. Second mode is anti-symmetric with respect to the middle cross-section. It's good to write down. Third mode is symmetric with respect to middle cross-section. Now, we can conclude that odd modes are symmetric with respect to middle cross-section. Odd numbered modes. Whereas even numbered modes are anti-symmetric. With respect to middle cross-section. Why does it happen? Because boundary conditions are symmetric with respect to middle cross-section. Now, let us see, please, what happened to our clamped free beam. Okay, this is a clamped free beam natural frequencies. So here we had the difference. Okay, so here we have clamped free, that is CC plus 1 equals 0. Clamped, CC minus 1 equals 0. Okay, so that is clamped free has transcendental equation CC plus 1. Clamped has an equation CC minus 1. Now, because for high frequencies, this for K is big, capital C goes to infinity, it is not important whether here is plus 1 or minus 1, because clamped free, this equation goes to C equals minus 1 over C, and clamped C equals 1 over C. But this goes to 0 and this goes to 0. So that means that asymptotically, these two beams have equal frequencies, equal high frequencies. Asymptotically, these two beams have equal high frequencies. So first frequencies are, of course, very different. First frequencies are very different. So it is 1875 versus 473. So these are very, very different values. Yes. Yeah. Second frequencies are closer. 2694. No, 4. Excuse me. 4694 versus. What did we have? Seven, 853. But other frequencies are already very close by. So we can say that these two beams actually asymptotically share infinite number of frequencies. Only first frequencies are different, but the rest of the frequencies are almost the same. It's very interesting. They are not exactly the same, but they are asymptotically the same. They're very close to pi times some even number, pi over 2 times some number. Okay, we will deal with beam with free ends. Beam with free ends. Or maybe before that, maybe you can cross this beam with free ends. We will have this discussion. For simply supported case, alpha L equals K times pi. So for clamped free case, so alpha L equals K plus 1/2 pi. Or maybe it's too fast. So clamped case is K plus 1/2 pi. So actually, pay attention, alpha L differs between these two cases by 1/2 pi. So here is K times pi, here is K plus 1/2 pi. So what does that mean? So imagine we have simply supported case. Okay, we have just K. So K equals 1, K times pi. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. These are simply supported frequencies. Okay? You may denote them as a big dot. So clamped is here. Clamped, clamped. clamped, clamped. Clamped are stars in between them. So we can say that, pay attention, first clamped beam case frequency is between first two frequencies which are simply supported. First clamped beam's frequency is between first two frequencies of simply supported beam. So this helps us to do numerical analysis. This 1 pi and 2 pi are associated with simply supported case. So between them there is one star. So between every two dots there is one star. So we can say that the interval whose length is slightly greater than pi, okay, interval, if I take an interval which length is slightly greater than pi, will contain at least one root for clamped beam. Because at least one. So if I take bigger than pi, so then the two roots here. And if I take this, only one root, etc. If I take any interval which is of length of a bit bigger than pi, will contain at least one root. It is an important observation for numerical purposes. Okay, you may want to write it down.